The last quantity that we need to consider for this introduction to kinematics is acceleration. We said that the position describes where the object is. The velocity describes how fast it's going and in what direction. We said the position needs to be changing so that the object's in motion. If the object is moving, then it will have a velocity. But if the velocity is constant, that means the object is just moving in a straight line at a constant speed, which happens in some situations, but is also kind of boring. There's not a whole lot going on in that situation as well. Here, we want to consider if the velocity is changing, and we would measure the change in the velocity via the acceleration. Acceleration is defined as the velocity's rate of change at some instant. And so at that instant, that is the instantaneous acceleration. And again, whenever you hear acceleration, it's assumed to be instantaneous, unless you're told specifically otherwise. A rate of change means a derivative, so our acceleration is the time derivative of the velocity. If we have a velocity graph, the acceleration at an instant in time is the slope of the tangent line at that instant. If we have a velocity function, you can take the derivative and evaluate the derivative to find the acceleration at that instant. Position was a vector. When we took the derivative of position to get velocity, velocity is a vector as well. When we take the derivative of the velocity vector, we get the acceleration, which is also a vector quantity. So it has two components to it. It has a magnitude. That magnitude is telling us how much the velocity is changing by, how much the object is speeding up or slowing down, and then the sign, whether the acceleration is plus or minus, is telling us whether the velocity is increasing or decreasing, right? What a derivative is a rate of change. It's telling us the change in that quantity. So the rate of change, the derivative of velocity, is whether the velocity is increasing or decreasing. That is not the same as speeding up or slowing down, though. If velocity is increasing, that means that velocity is becoming more positive. If the velocity is decreasing, that means that the velocity is becoming more negative. That's what it means to decrease. So if the velocity is a very large positive number, and that large positive number becomes more negative, that means you have a smaller positive number, which means that your velocity is a smaller value, you're slowing down. But if the velocity itself is already negative, and then the velocity decreases, which means your negative number becomes even more negative, that means it's a bigger negative number, and and that means you're going faster, but faster in the negative direction, faster to the left. So the sign, SIGN sign of the acceleration, is not telling you whether you're speeding up or slowing down. We're going to see a little bit later how to find speeding up or slowing down. Also, velocity is measured in meters per second. Time here is measured in seconds. And so what our acceleration is measuring is how many meters per second of velocity change are you seeing per second that elapses. And so meters per second is generally seen as meters per second squared in the SI system, or feet per second squared in the imperial system. Beyond the instantaneous acceleration, we can also find the average acceleration, mirroring what we saw for the relationship between position and velocity. Our relationship here between velocity and acceleration is still a rate of change. So the average acceleration is the average rate of change. That's the change across a finite time interval, and it's the total change in velocity divided by that finite time interval. So instantaneous acceleration is a derivative, an infinitesimal change in velocity and an infinitesimal change in time. Average acceleration is a finite change in velocity over a finite change in time. We saw that this thing here is the slope between 2 points. This is the slope of the secant line of that velocity graph. We also can find the average acceleration using the average value theorem. If you have an acceleration versus time, you can integrate across the interval. If you divide by the width of the interval, that gives you the height of the function over that interval, that average value over that interval. Again, that's the average value theorem. You've seen that in Calc 1. When we put all this together, we can include our acceleration in our motion diagram that we talked about at the very beginning. We have our coordinate axis, where we're coordinate system that is allowing us to describe the position. We have these particles representing the location of the object. Technically, we should have position functions or position vectors pointing to the location of the object at each point, but you can see how cluttered that's getting already. And since the particle is already shown, its location is already shown, there's implicitly a position vector for each particle. The velocity vectors, the average velocity vector, points from one particle to the next, to the next, to the next. Basically, these average velocity vectors are overlaying the displacement. If you were here and later on you're there, that's your displacement. And so your average velocity is going to be proportional to that. If you're here and later on you're there, that's your displacement, and your average velocity in that interval is going to be proportional to that. And then we said that the average acceleration is looking at the change in velocity per time. So what we're doing here to have the acceleration vectors, we're average acceleration vectors in our sketch here. We look at the velocity after we're at this position, which is 4 in this case, the velocity before we're at that position, which is 2, and the acceleration is the difference between the 4 and the 2. It's proportional to that, so we just draw it as a 1-to-1 proportion. For example, here we have an average position here, our average velocity here, this average velocity before and after we're at this location is the same. This velocity is the same as that velocity, so our acceleration is 0 at that point. Our velocity is not changing in this interval here. Our velocity is constant from here to there. And then notice that the velocities are getting a little bit shorter each time, so a smaller positive number minus a larger positive number gives us a small negative number. And so by looking at our complete motion diagram here, we can see that from the arrows, we're moving to the right, we're speeding up, we're moving at a constant speed for a short time, and then we're slowing down, but we're slowing down at a smaller rate. So again, we have our velocity increases, our velocity is constant, and our velocity is decreasing. If our velocity is decreasing with positive velocity, we have that small negative acceleration. Velocity is the derivative of acceleration. So if we know the velocity, we can take the derivative and find the acceleration. We should be able to reverse that as well. If we know the acceleration, we should be able to find the velocity. If acceleration is the derivative of velocity, then velocity is going to be the antiderivative of acceleration, but it requires an initial condition. Same as before, whenever we're doing an integral, we're always going to have a plus c, and we need an initial condition to be able to nail down what that plus c is. So if you integrate your acceleration, it gives you back velocity, but you get a plus c, and you need to know the initial condition. You can also do a definite integral. This is looking at the change in velocity per time, and then times time gives us the little bitty change in velocity during each little dt. When we do the integral, when we add those up, we find the total change in velocity. So our definite integral gives us the change in velocity during that interval. It does not tell us the velocity back. But if you knew how fast you were going at the beginning, and you know how much the velocity changes, you could work your way backwards to find out what the velocity would be at the very end. And lastly, we said that whether the acceleration is positive or negative does not tell you whether you're speeding up or slowing down. Acceleration is measuring the change in velocity, so it's telling us whether the velocity itself is becoming more positive or negative. So if you have an object that is moving to the right, and that object has a positive acceleration, our positive velocity plus positive acceleration is going to give us an even greater positive velocity. So this is speeding up. We could make the same argument if we were moving to the left, and we had a negative velocity because we're moving to the left, and a negative acceleration. That would give us an even greater leftward acceleration. So what we're seeing there is that we're speeding up, not when the acceleration is positive or negative, but we're speeding up when the velocity and the acceleration have the same direction, which for now means the same signs. If the acceleration and the velocity are both positive, we're adding positive on a positive number, which gives us a bigger positive number, a faster speed. If we're adding negative change to a negative value, that gives us an even bigger negative value, which means we're going faster, but faster in the negative direction, faster to the left. If the object is moving to the left has a negative velocity and a positive acceleration, that means that we're going to have a more positive velocity, means a smaller negative velocity is the same as a smaller negative number is bigger than a larger negative number. And so this is a bigger number. This is more positive than that. But our velocity itself is a smaller value. It means we're going more slowly to the left. So we're slowing down if the velocity and the acceleration have opposite signs, if they're pointing in opposite directions.